with my hand woggling up and down? Yes would be good.
Yep.
Okay, good. As you know, I don't actually always, I can't always tell what you're saying, and sometimes I talk away quite happily pointing at stuff and none of you can see what I'm pointing at, which isn't much fun for you. Okay, let's get started. This is your last section that you need to do for your test, which will be on Sunday at midnight, as always. What else do I need to tell you? I'm going to be shooting out an email sometime, hopefully today if I can remember, and definitely in the next day or two. And it's just going to ask you what time from noon till 2 on week 10, Tuesday, Wednesday, Thursday or Friday, that you are available. And then I'll take, hopefully there is one day out of that lot that nobody's doing some other test. And that will be the time slot for our final. So let's get started. Well, the section's called surface integrals. As you know, I'm a horrible artist, but I'm trying my best to show you what a surface integral is. Can you imagine that the surface here, this thing here, is written down as, you know, maybe z equals a function of x and y. But it could be written as x squared plus y squared plus z squared equals 10, you know, whatever it is, right? It's a surface in 3D space. Now, a surface is like an infinitely thin piece of wavy paper. Now, a surface integral takes a small piece of that surface, which I'm now shading in kind of red, and it looks at all the points on that surface and it calculates the integral over that region. So it's not an integral over a line, that would be a line integral. It's a double integral, right? Because it's an integral over a two-dimensional space. It's a two-dimensional space in 3 dimensions. So can you imagine that was a piece of paper? It'd be kind of, I don't know, it might look like what's that word? A peanut, like a cross-section of a peanut kind of shape, beveled on an edge and bent. But it's still a 2D surface. You know, this piece of paper is a 2D surface, right? If I bent it, it's still a 2D surface, right? So maybe that's a better analogy, right? It's like a curved piece of paper. And so that red bit is the S that they're talking about. And then you evaluate the function, whatever the function happens to be, x squared plus y squared plus z squared, whatever that function happens to be. So that function, oh, here's an idea. Can you imagine that the surface, at every single point in that surface, it had a temperature? If you do the surface integral, you're essentially adding up the total amount of heat energy in that piece of metal, that surface piece of metal. So you're adding that up. So, theory. How do you get a line integral? Or I should say a surface integral. Well, it's described as a double integral over the surface S of some function, x, y, z, ds. If you make this function 1, right, just the number 1, do you know you're actually calculating the area of the surface S? But most of the time, this here would be x squared plus y plus z or something. So you're going to do a double integral, surface integral, over the surface S of some function x, y, z, ds. And the formula says you can convert it into a different double integral that does the same job. It's still got the function f, x, y, z, and it's got this little extra bit here. You square root of that guy squared plus that guy squared plus 1, dA. And dA is a placeholder. dA is for dx, dy, but sometimes you'll use polar, and it'll be a placeholder for dr, d theta, right? R, dr, d theta. Now, what's region D? Well, this is also quite visual. Can you imagine the surface that I had here? Can you imagine shining a light down to the floor? The D is the region in the XY plane that that surface would project onto. Now, in a lot of questions, they don't ask you to evaluate that thing, and they just tell you what it is. And most of the time, it's a rectangle or a triangle when they tell you what it is. But occasionally, you will have to figure that out. Now, if you're wondering, how do you figure that out? Well, there's an example. Suppose that, I know that shape isn't, but suppose that shape had this formula to it. If you make z equals 0, do you see that it becomes a circle, x squared plus y squared equals 10? So if you want to know what a surface looks like, just make the z 0, and that's essentially what the projection would become. Well, let's put it into operation. I think that's, the devil is in the detail. So we've got a plane, right? That's basically describing the red shaded bit, right? This bit here, the region that lies above this fella, this bit here is describing D. Basically, it's a little rectangle on the floor. So the surface integral of x, y, z squared ds is equal to the double integral over this region, I'm just going to call it D right now, of the same function, the square root of the partial derivative of z with respect to x squared plus the partial derivative with respect to y squared plus 1. And if you're wondering where the plus 1 comes from, it's actually kind of cool. The z by dz would be the next term, wouldn't it? You did it with x and you squared it. You did a partial derivative with y and you squared it. So guess what dz by dz is? It's 1. And then you square it. So it is kind of symmetrical, right? There is a kind of symmetry to it. It's just that that ends up always being 1, at least in this particular projection. So what do we have? These numbers represent the values of x. This represents the y. So just because I'm writing it this way, I'm just committing myself. So x equals 1 to 2. And this is me describing region D. This is going to be y equals 0 to y equals 1. The function is x, y. Our first little hiccup. We have a z squared here. But for this integral here to work, you can only have x's and y's, right? The z's have to be eliminated from the expression. Now, that doesn't mean you make them 0. It means you replace them by what it is worth. And you see up here, z is 2x plus 3y plus 1. So z squared becomes 2x plus 3y plus 1 squared. Are you happy about what happened there? Right? Essentially substitution. Followed by square root of dA. Right, okay. If you take this guy, and this is the guy we're talking about, and you do a partial derivative of him with respect to x, you get 2, and then you square it. If you do a partial derivative of this guy with respect to y, you get a 3, and then you square it. Do not do the partial derivative with this guy. It's a partial derivative of the surface, right? This fellow over here. Not ever this guy. Always the guy with the balloon round. So what does that look like? Well, it looks like the integral from 1 to 2, the integral from 0 to 1 of xy, 2x plus 3y plus 1 all squared. That's 1, that's 10, square root of 14, dy dx. And you recognize why I'm going dy and dx, because of the limits of integration. Right, now this guy here is horrible, this guy here is messy, this guy here takes a long time. The only good thing about it is that this guy here is easy. Won't you just FOIL that whole thing out, multiply by xy, and won't you just have a huge, big, long polynomial with x's and y's in it? And we all know how to do double integrals with x's and y's, right? Just takes time, it doesn't take effort. So can I dot that and call that one good? It's got a nice process, doesn't it? It's got a nice formula. You just got to figure out where the bits and pieces all get changed in. You should be fine. Any questions about the first one before I move on? Okay, I'm assuming that is a good sign. Next question I'm going to do looks like what? The double integral over the surface S of x squared z plus y squared z ds. S is a hemisphere, that means it's half of a sphere. And it's x squared plus y squared plus z squared equals 9. I could probably draw that surface. Okay, I can't draw surfaces. Does it kind of look like half a sphere? No, be generous, right? Kind of half a sphere, right? Now, what else do we know about this fella? Well, we should be able to figure out who D is. If you take that entire surface, right, and you project it onto the floor, essentially, don't you just make z squared 0? And what you're looking at is a circle. So could you imagine, probably going to really make a mess of this thing now, that on the floor, the XY plane, you've got a little circle. And D is that circle that's on the XY plane. So far, so good? Now, I know all sorts of bits and pieces going in here, so it's going to be the double integral over D, the square root of dz by dx all squared, plus dz by dy all squared, plus 1 dA, and I forgot to stick it in. So see those 3 little dots? That guy. Not only did I forget to stick it in, I don't have enough room for it. So if you wait patiently, I'll actually rewrite it the way it should have been written the first time. Okay, at least we've got to the point where we can now start thinking about putting in the details now, all the little bits and pieces. In this particular case, my brain is looking at this region D. And when I look at this little region D, something comes to mind. Do you think I'm going to go polar, or do you think I'm going to go XY? All right, I see Rachel's lips moving and she's saying polar, so I'm going with that. Agreed? Right. So, how are we going to figure this thing out? Well, first I'm going to turn everything into x's and y's and replace the z with x's and y's, and that's going to be really messy. And then I'm going to go polar once that's out the way. So, if you start with x squared plus y squared plus z squared equals 9, that gets you z squared is 9 take away x squared, take away y squared. So far, so good? Which means that z is the square root of that guy, which I'm going to call a half power. Now, I need to know its partial derivative and square it with respect to x. So here goes. The partial derivative with respect to x is 1/2 9 minus x squared, take away y squared, to the power of negative 1/2 times something. Think chain rule. What should I multiply by?
negative 2x.
Now, all I'm going to do now is tidy it up. Not much, but you do the best you can. Are you happy about the 2.5 cancel? The negative's still there. There's an x on the top, this guy's in the bottom. And that's only to get to there, right? Now, I know I'm going to square it, so I might as well do it right now. If you square this, you get x squared on the top, and you get 9 take away x squared, take away y squared on the bottom. Are you happy about what happened there? Great. Now, I'm going to use symmetry. Can we just assume that that's pretty obvious that, you know, the first one gets you that, the second one will get you that? Now, this mess over here is going to get converted into nothing but x's and y's first, and then we'll figure out the polar afterwards. So let's see what we have. So it's going to be the double integral of x squared z. Oops, already start off at a bad place. Let's do it that way. I'm just pulling out a z right now. I don't want to do too much. Square root of first guy. Plus the second guy. Plus 1 dA. Now, the reason I kind of pulled out a z here, and it was kind of last minute because I only noticed it in last minute, is shouldn't that z be turned into x's and y's as well, like everyone else was? In fact, it should be turned into this guy. So I now have the double integral of the square root of 9 minus x squared minus y squared times an x squared plus y squared times the square root of, if you take this guy and you add 1 to it, you will get something relatively nice looking. If I want to add 1 to these two fractions, don't I need to convert the 1 into a very special version of 1? 9 minus x squared minus y squared over itself. But they cancel out those two guys, and can you trust me that when you're finished, you just get a 9? So that 1 converted into 9 minus x squared minus y squared over 9 minus x squared minus y squared kills off the x and y squared, and you're just left with a 9. Now, this fella is getting quite nice. I know he's not there yet, but he is getting quite nice.
We have a cancellation. I like it.
Yes. Because the square root of 9 gets you 3, and the other guy, when you separate the square root into its two parts, gets you this, and we've got a dA, and just like you mentioned, cancel. 3 lots of x squared plus y squared dA. Now, in this question, I think polar lends itself really well, because the trick here is, for this circle, if you do it in polar form, if you describe D in polar form, won't R be from 0 to 3? And theta will be from 0 to 2 pi. So it means I can go from 0 to 3, 0 to 2 pi, 3. What will that little x squared plus y squared become when you go polar on it?
R squared.
Yeah. And won't we get another r dr d theta? And so I could split this as a 0 to 3, 3r cubed dr, with a 0 to 2 pi, I guess essentially, of 1 d theta. And at this point, I'm dotting it.
That just came out really nicely.
Yeah. That's why you let textbooks make up questions. If I just randomly pick some stuff, it ain't going to come out pretty, right? Or very rarely is it going to come out pretty. But do you get the grasp of how this process is beginning to develop? It's quite heavy. Sometimes it's quite heavy, as it was here, and just fighting your way through. But very often there's a nice little dessert at the end, something nice and sweet, like, oh, that's kind of cool. Now, I'm going to call that question good, unless there's anyone want to ask something more about it before we move on. So right now we're calculating these things called surface integrals. I was looking over some of the work. I'm not an engineer, but evidently these surface integrals are very closely related to a thing called flux. And evidently fluxes of force fields are interesting for people who want to find out what fluxes are. I find it very difficult to feign enthusiasm for something I'm not. But evidently you engineers are going, oh God, you can get fluxes with that? That's great. Just see if I can pick another one. Again, I'm trying to make sure I pick something that's in my list here, but I'm never quite sure if I picked one until too late, and then I don't want to get all caught up. Okay, I'll tell you what, I know what I'll do. The simplest way for me to do this is that we will go and look at the homework, and I'll pick one. So, share screen, go into basics, and I think it's this one. Oh, right, so we do have all sorts of examples of this thing. What's going on? It's a plane, I guess I could do that one. There's a semisphere. It's a weird one. The first octave one. Oh, let's do a triangle one. No particular reason. So this is question 8. We're doing a surface integral of something very simple, x. And S is a triangular region which goes from 1, 0, 0. Then it goes 0, negative 2, 0. And then it goes finally 0, 0, 16. My experience has been whenever you see a question that looks really easy, it's probably not. I mean, x dx, I mean, x ds, I mean, how bad could s be, right?
Probably pretty bad.
Probably. I don't know this question, so I'm kind of doing it blind, but that's fine. Really, we know what it's going to become, right? It's going to become a double integral of d of x with dz by dx squared plus dz by dy squared plus 1 dA. So there are two problems that are not self-evident right now. Problem number 1 is, I do not know who you are. This here is a surface. I'm pretty sure it's a plane in 3D space, right? It's an angled flat piece of paper in 3D space. I need to know who you are because you're the guy that's going to get differentiated with x. You're the guy that's going to get differentiated with y and squared right and added 1 to it. Second thing I don't know is, I don't know what that guy looks like when he gets projected down onto the floor. Right? I need to know what that region looks like. So I have two distinctly different problems. First one, find the equation of a plane that passes through 3 points. And that's the first thing I'm going to tackle. Then once I've got that, I'll then have to figure out what region D looks like. Now, my brain is telling me that if you join these 3 points together, you'll generate a plane. Agreed? But 3 points in that plane, won't they represent a triangle on the floor? Right, if you project that triangle on the 3D plane, won't it look like a triangle on the floor? Won't be the same triangle, you know, like the shadows are not the same as the object, but it'll have the same shape.
If you're projecting it onto the XY plane, it should be go from 1, 0 to 0, -2, and then back to the origin.
Oh, we could do that first then. I was going to do the plane and then the projection, but let's do the projection. Right. For those who can't see what he just said, I'm writing down these points just again, so I can point at them and write all over them and not make a mess of the original. You imagine this here, it's 1, 0, 0, 0, -2, 0, and 0, 0, 16. But when you look at it from above looking downwards, don't the Z coordinates make no difference? Because no matter what height it is, won't it land in the same place? So I'm assuming that that's where you got 1, 0 to 0, -2, 0, 0 from. Is that your thought process, or did you see that a different way?
That was my thought process, really. Just remove Z.
Remove Z and you can see it. Are we comfortable with what I just did there? I've actually described D. In fact, I'm going to draw the darn thing. There's the origin, there's 1, 0, and there's the other one, right? So that's us now got a picture of D. That's half the problem done, right? Now I get to do my little sentence again. You think that you will never need to do insert name here ever again in math. And I say, nope, you're wrong. So here's another one. We are going to find the equation of a plane that passes through 3 points in three-dimensional space. And that is a Calc 3 question. Can anybody start that process off for me? So we're about to find the equation of a plane that passes through 1, 0, 0, 0, -2, 0, 0, 0, 16. So, can you pretend that that's the 3 points in 3D space? And we want to find the equation of the plane that generates that. Where do I start? Calc 3, equations of planes. Any bells ringing yet? Any light bulbs? Okay, I'm going to call this guy A, I'm going to call this point B, I'm going to call this point C. I'm going to find the vector joining A to B and the vector joining A to C. The vector joining A to B is -1, -2, 0. The vector joining A to C is -1, 0, 16. So if you pretend that's A, I've just found this vector here and this vector here. So far, I am about to calculate what we would call the norm, the normal. It's a vector that's perpendicular to the plane. So in this case, it's going to be the vector perpendicular to those two guys.
Wasn't the two vectors crossed with each other?
Yep, so that's where I'm off to now. The cross product, which I'm going to call N, is the cross product of these two guys. I think this question is living up to the simplest questions end up being quite messy. In this case, I'm going to go -1, -2, 0, -1, 0, and 16. And it's so many i's, taking me so many j's, plus so many k's. For instance, you've done this for a different reason, right? A few days back, remember doing these guys? So what do you get? -32 take away nothing is -32. -16 take away nothing is -16. And 0 take away 2 is -2. And so this fella is -32, +16, -2, and we now have a normal vector. We're getting there. Where do we go now?
Well, from there, we'd have to find the equation for the plane that that vector is normal to,
Right?
with the points that we have
Right.
as points on the plane.
Correct. That's as far as that's as far as the process is going so far in your head, right?
And so far, that's all I got.
Okay, it's a good start. Everything you said is true. We have to figure out what you said is how we use the information that we have. Well, typically the theory says, pretend there is a random point called XYZ on the plane. Now, if you join that guy to this guy, won't those two be at right angles? Because one line is on the plane and the other's normal to the plane. And if they are at right angles, doesn't that make their dot product 0? Okay.
Right.
So I'm going to use the point A with coordinates 1, 0, 0. I'm going to use another point, R I'll call it, called XYZ. Then won't the vector AR cross product with N be 0? And that gets me X take away 1, Y, Z, dot product with -32, 16, -2. That gets me -32 X minus 1s plus 16 Ys take away 2 Zs equals 0, which in turn gets me -32X plus 16Y take away 2Z equals 32. I guess I could divide everybody by 2 just to make it a little bit prettier. And if I did that, I'd get -16X plus 8Y take away Z equals 16. And with a little bit more rearranging, bingo, almost ran out of paper. Which means I can now go back here. The finish to this is going to be dead relatively easy. I can't say dead easy because it won't be. Double integral d of x. If you differentiate this z with respect to x, you get 16, so it's 16 squared. You do a y, it's -8, so that's -8 squared plus 1. That's going to get you the guy that goes there. It's going to be the double integral of d of 256, 260. Oh, God in heaven.
Hold on a second.
Thank you.
Wouldn't the z be equal to negative of the equation that we currently have because it's a negative z?
This one here, let's check it. I moved that over and moved that back, so you're right. Well, that's just basically, thankfully it doesn't change anything here, so apart from, that's negative and that's plus. So 16 squared is still going to be my doing number. So 16 times 16. Going to add another 64 to that. Then I'm going to add 1 to that, and I'm going to get square root of 321. So we're looking at the square root of 321x dA. And D is a little fella down here. And so I'm going to do my little triangle, my little vertical rectangle. I guess I should put the numbers in here, shouldn't I? There we go. And that's going to give me the fellas that are going to go here. So I guess I need to know what the straight line is as an equation. If you go from here to here, what do? You go 2 up and 1 along, so it's a half. What, a half take away 2? Are you happy about the equation of that line being a half x take away 2? Because I'm not, because I've just realized I've done something wrong. I can't do things quickly. How about 2x take away 2? Does that look good? So our integral is going to go from y equals 0. Which one? Top and bottom. I guess I should get the size right. Y equals 2x plus 2. And x is going to go from 0 to 1. And then I can do dy
2x minus
dx.
2?
Say that again?
You mean 2x minus 2?
Yes. And there's something else in here. 321. Oh, and there's an x. Right. That's pretty much where I'm going to dot that one. They do mention in some of the questions that there's a positive orientation and a negative orientation. And so if they say it's a positive orientation, typically you make your integral exactly as I have, technically with a plus at the front. If it is a negative